Hey, this is OXDF. Thanks for joining me today. Today, in prep for the 2023 cyber apocalypse, we're going to go over two of the forensics challenges from the 2022 cyber apocalypse because, learning the skills necessary last year is probably going to be helpful going into this year. We're going to look at two types of challenges. One of them is looking at a Windows registry file and finding the persistence and then decoding and breaking down what was going on there. And the other one is looking through a PCAP and finding some DNS exfiltration and understanding how it's happening, decrypting the data, and finding the flag in there. So all in all, hopefully it'll be a fun time, and let's go ahead and jump in. So we're going to look at the challenge Golden Persistence from last year's Cyber Apocalypse CTF, and we'll go ahead and read the prompt. Emergency, a space station near Urker was compromised. Although Urker is considered to be the very embodiment of a neutral state, it is rich in fuel substances, something that Draeger is very interested in. Thus, there are now fears of intergalactic war that will also affect this neutral planet. If his mercenaries are able to maintain unauthorized access to the space station and escalate their privileges, they'll soon be able to activate the station's defense mechanisms that are able to prevent any spaceship from entering Urker's airspace. For now, the infected machine is isolated until the case is closed. Help Miyuki find their persistence mechanisms so they cannot gain access again. And so we have a download here, and we'll jump over to my Linux VM here and just take a look at it. And inside the zip, we get a single file ntuser.dat. Now on a Windows host, the registry is a complex system, almost like a database in the OS, where you can maintain preferences and settings and all sorts of things. All sorts of programs read and write to the registry. And it's why you can store things between activations. So specifically, when we start talking about persistence, there are tons of places across the registry that you could write in such a way that when the box reboots, you get some execution, or when a user takes some action like clicks a mouse or opens up a Explorer, some action happens. There's one that is the most famous and is known as the run key. Now there's copies of the run key in both the system-wide registry as well as in each user's per user parts of the registry. The system-wide registry keys are stored in files in C Windows System 32, and then each user has their own registry file in their home directory, ntuser.dat. So we're given an ntuser.dat file. We can check out and see what we have here, and Linux is going to tell us that this is a Windows registry file, so that's what we're thinking. And so what I want to do, what I'm thinking here is I want to find what are the most common places to go check for persistence. And so since the run key is the number one, I'm going to go there. And if that doesn't work, we'll start exploring, looking up, maybe going into MITRE ATT&CK and looking into registry persistence and seeing what other things might show up. But we're going to start there. In fact, let's jump over to a Windows VM. We're going to solve this in both Windows and Linux, but I'm going to show you Windows first. So golden persistence here. I've got the file as well as some shortcuts we're going to use. We'll go ahead and use Registry Explorer. This is a tool from Eric Zimmerman. It's free to download, and it is just what it says. So we're going to load a hive from desktop, golden persistence. We'll give it ntuser.dat. The primary and secondary sequence numbers do not match. Basically, something is out of whack here. That's fine. We're just, do you want to replay the transaction logs? We'll say no, we're not going to replay anything. It's a dirty hive. Do we want to load it? We'll say okay. And we've got our hive here. Now it starts at root. And we can open it down here and go here. Now, normally this would be mounted as like HK current user, where you'd see this mounted, but because we're loading it offline, it doesn't really make sense in that context. So we just have it here. So the run key is in software, Microsoft Windows, current version, and then run right here. And so if we click on this, make this a little bit bigger, we can see in the run key, we've got OneDrive here, and we'll look at this first because it looks probably like it's legit. And so we can see on boot, this user, I guess it's on login, whenever this user logs in, we are going to want to run OneDrive. And so specifically in the user's home directory, grep app data local Microsoft OneDrive one.exe/background. So that we're going to start Microsoft OneDrive in the background. Well, it seems legit. I mean, we could investigate that binary and see if that's really OneDrive or if something they put there, but that seems potentially legit. Similarly, running program files, Microsoft Edge application, some sort of background Edge thing seems potentially okay. But then we have this one here, VH0 F7 blah blah blah, and it is going to run Windows PowerShell with an encoded command that looks just a long encoded command. Now, of these three, which one is the suspect one? The encoded command. So we're going to start there. Let's go ahead and grab this. We'll just select all. I'm going to jump real quick over to CyberChef. CyberChef is, the Swiss Army knife of solving CTF challenges and just other random things. We'll get rid of the PowerShell call so that we just have this base 64 encode data, and then we can just say from base 64, and we get this nice stuff. Now, Windows uses a 16-bit character instead of an 8-bit character, and that's why every other dot here is displaying it's basically a null byte. And we can get this real simply if we just get the decode text, I believe it's called. Yeah, here, decode text, and we say the encoding is 16-bit little endian, and now we have a nice looking script. Let's come here, and the other thing, we're going to save this. I'm actually going to use Visual Studio Code here to analyze it, and it's nice because it's going to give me syntax highlighting and other, it'll be easier to deal with in here. So we will open up, let's see, we're going to go to open folder, desktop, golden persistence, select folder. And now we've got our stuff in here. We're going to say we trust the authors, even though we don't really, even though we don't totally trust them, we're just going to be careful. And then we're going to come up here and add a file, and we'll call this golden.ps1. Paste that in. And so now we can see, what do we have here? One thing I always like to do when I'm just quickly trying to figure out what's going on is to shrink down the functions. And so now we can see basically of these 73 lines, we really only have these two functions, one called encrypt probably, and one called hex to bin. And then we have the stuff going on down here where we're going to get a key. We're going to read. These are each different, read basically 5 different values out of registry, and then append them all together into something called encrypted. We're going to then hex to bin encrypted, which is this function here, which maybe we just assume for the moment that it does what it says it's going to do and turns hex into bit binary. Then we're going to call encrypt on data with the key. And then we're going to get a string from that, and then we're going to pipe that string into IEX to execute it. So this is a very kind of typical malware behavior. But I suspect if we can get this downloaded decrypted string and get these values here, we'll be in good shape. So let's go ahead and check it out. We aren't even going to look. We'll come back later and look at these functions, but for now we're just going to try solving it. When I solve it in Windows, I'm going to solve it one way here. So what we're going to do is my registry is not going to have these registry values. So what we're going to do is come up here and comment that out, and we'll say encrypted 1 is equal to, and then let's go find this value right here in HKU software. Best way I can set this up so I can see both at the same time. Yeah, over here. Okay. Software, way up to the top. Shrink this down, shrink back up. We don't need the Microsoft one anymore. Software B right here. And we can see we have a value right here on the side. So we'll grab this and, oops, that's the wrong, I got the second one. So we'll come down here and do encrypted 2 equals that. We got that nice and nicely. Count that out. Let's get encrypted 1, which is the software and the one that starts with Z, so right here. And again, it's getting the one that starts with Z, and then this value that starts with T is the value name here. So we see that, and then we come down here, here's the value name again, and we can grab the value up here, paste that in. So I've got 2. I'll do this just a couple more times. I guess in some ways it was nice of the challenge author not to give us like 10 keys under here and make us figure out which one it was. They probably didn't need 5 keys because like once you prove you can do this once, you can do it 5 times, but okay. So that's looking pretty good. Now we've got those there. Now we're going to make an assumption, and this may be wrong. We're going to try that calling, it seems like we're passing the data into the encrypt function and getting decrypted stuff. Since that's what the script is doing, let's just assume it's going to work because it is trying to eventually execute that. So we're going to run that. We were going to edit our script a little bit here so we get rid of this decrypt string. Now we're going to print decrypt string instead of executing it, which is what we want. And let's see, maybe perhaps we can write this. Let's see. Let's see, where are we? We can go into golden persistence, stir, nothing there. That's weird. Let's close this terminal. Maybe I have a bad terminal. Actually, let's try this. We're going to hit F5 here to start running, and we are hitting errors all over the place. One thing I'm noticing, let's see, what's the first error we hit here? Cannot call a method on a null value expression, line 62. Yeah, interestingly, enc is created here, or is called here, but it's actually used down here. And it looks like it's necessary. I'm going to pull this here and move this here. Because enc get bytes is a function that exists on this system text encoding thing, but we need to specify it. So let's try that and see if that helps. That didn't help me. Let's F5 here to run this. And F5, let's run this again. It runs. It's not printing. Maybe we need to let's put a breakpoint here and try that. F5. Now run to the breakpoint, and we can say, what are our local? Is it our local? Oops. Command local decrypted string is right here. Nice. We can go to the debug console and put rypt string, and it prints to the terminal. Okay. And we can see right here, I'll pull this into a new PS1 file just so you can see it, but here, new file, stage2.ps1, paste this in, and we can Control H, and we want to find and replace semicolon with a Shift Enter will give me that, and we can replace all, and then I gotta get this one that I accidentally did manually. Okay, and so basically we're gonna get a path for some executable. We're gonna test if it exists. If it exists, we're gonna start the process. Else, we're gonna make the directory and try to download it, and we have our flag here, so we get the flag. But we basically figured out exactly what it's doing too. So we've really solved the challenge as well. I'm going to jump over now to my Linux VM and show you real quickly how we can do the same thing without access to Windows. I'm going to use a tool called reg lookup, and this is you can apt install reg lookup. And basically, there's a couple ways you can run this. If we do a -p, and then we can do software, Microsoft, Windows, current version, run, and then give it mtuser.dat, we get that junk. You can see here we get all of the different things in the run key. I'm gonna try this one. I'm actually gonna pipe this into less-S. And so you can see we have each of the values. So we get the key itself, and then each of the values sitting in it, along with their values. Less capital S just doesn't line wrap, so I can go view this all the way, goes way over the edge. So I got that there. We could, let's see, what's the best way to do this? We could save this to a file here and call it like output, and then vim output, and we can real easily delete, get rid of this so we have just the base 64 here, and then we can mess with it again. I'll leave that as an exercise for you guys. The one thing I do want to show though is, so once we have that data, I'm gonna come back over here just because I happen to already have it in VS Code. We never looked at like hex to bin. It's actually pretty simple. It's just getting hex stuff and converting it to binary. So nothing super interesting there. But what is the encryption function actually doing? This is actually RC4 encryption. There's a couple ways you can recognize this. RC4 always starts off with creating a vector, like an initialization vector that's a key function it's going to use, that's always 256 long. And so you can see that there. And then it loops over the vector and adds the current byte to that value plus the key value and mods it 256. And this is just like what RC4 does. So if you can recognize that, like always look for two loops, and in the first one where it's initializing something to the values 0 to 255. And then later it then loops through that and mods it. Those are the kinds of things you want to look for RC4. So if we know that, we can grab this. Let's see, copy this. I was going to go back to my Linux VM, but we could do this on Linux too. We can come here and say paste that in. Let's grab our four values here, which we could get out the same way. In fact, I'll show you real quick just to show you. Let's say we wanted to get this value out. One thing that's kind of neat you can do, I mean, I could put that whole key in. Alternatively, oops, get out of here. I don't need to save this. Alternatively, I can call reg lookup. In fact, let's just clear reg lookup into user without that, and it's going to print the entire registry. And so now I can use things like grep to get like, oh, I'm just looking for this thing. Great, here it is, and there's my key value right there. So I could grab this value and the other ones just using reg lookup. And once I have all those, now I lost track of where I was. I think I did 2 of them. See, we end in 4BA1, which is that one. So we'll grab this one. This one. And one more. And now, we don't need this from base64 anymore. We don't need to decode text. So what do we want to do? We want to hex to bin. So from hex, I believe it's called. So we'll do that. And now we got binary stuff here. And then RC4. And we have a passphrase, which was in the code right there. We put that, we get the script, we get the code, the flag, and we solved it. So again, this is in the Windows VM, but we could have done this whole thing in Linux and it would have been just fine there. So that is golden persistence. All right, let's take a look at automation. Start with reading the prompt. Vinri's threat intelligence is closely monitoring all APT groups from every possible galaxy, especially the most dangerous one, long here. It's stated by an anonymous threat intelligence officer, the malicious actors tend to automate their initial post-exploitation enumeration so they can have less on-keyboard time. You can find such an example in the network capture provided, generated by a recent incident. Analyze it and find out what they are up to. So we do have a downloadable file here. We'll click and download, and I've already got it here in my VM. We can take a look. It's a PCAP file. Well, there's a zip, it has a PCAP file. So we'll go ahead and open up in Wireshark. Control O, we got a capture here. And before we look at any packets, I always want to start looking by statistics. So we'll start with the protocol hierarchy. If I can make this any bigger, we'll zoom. It's all Ethernet frames, IPv4. Under IPv4, we have UDP and TCP. On the TCP side, we have some TLS, so that's going to be like a HTTPS connection. There's 194 packets there, and then there's some HTTP as well, including some data and a media thing. So we'll want to check those out. Also under the UDP side, there's 168 DNS packets, which seems rather high. You know, a standard HTTP or HTTPS is going to take, you know, multiple packets, and we have basically the same number, maybe a little bit more, but not almost as many DNS queries as we do, you know, HTTP packets. Like, that's pretty odd. We'll want to look into that. All right, let's close this. We also have the conversations. Is another one to look at. Let's start with the IP. So we can see right away 10.0.2.15 seems to be like our centered point host. Maybe it's our host that the infected host that we're on, probably capturing from. And then we have a bunch of other hosts we talk to. Under TCP, what jumps out at me right away is all the packets are going to either 80 or 443. So it's going to be all HTTPS or HTTP. We're not going to worry about the HTTPS. Probably we won't have the means to decrypt that. But we'll definitely check out the HTTP. If we sort by bytes, we can see we have 3 large HTTP streams and another one down here that's, I guess got some size to it, but we're getting pretty small at this point. And maybe this 4,000. Under UDP, this is interesting because usually what I expect to see when I look at a PCAP from a host is that it typically is going to talk to one DNS server, right? And like in your network, like 192.168.1.1, or maybe your ISPs, but you know, once I see it talking to 192.168.1.1, that seems like the DNS server. So what is this 147, 182, 172, 189 host? And there's a lot of requests going to that host. So that's something interesting we're going to want to check out as well. We'll go ahead and close this. I'm going to do this PCAP is pretty small in size. And so really just to make sure I'm not missing anything, I'm just going to step through the streams. If I hover down here, I can see there are 30 total streams. So that should take me, this should be pretty quick, right? This is classic TLS looking behavior. So they're exchanging certificates, and that's what we're seeing the strings here, but the rest of anything useful will be encrypted probably. So more encrypted stuff. Here we have a download from windowsupdate.com. It seems like it's probably Microsoft owned. We could write that down and come back to it if we don't find something else, but I'm going to assume this is probably not interesting. Another download from windowsupdate.com, partial content. So this looks like it's probably a continuation of the previous one. Same thing. TLS, 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 nothing, nothing, TLS, TLS. Now this is interesting. We're getting desktop.png right here from Windows Live Updater.com. That is different, and that may or may not be Windows owned. What jumps right out to me? Do you see it? Do you see anything weird with the data that's claiming to be an image here? One, it's all ASCII text. There's no bytes. You know, if you have an image, it's going to have bytes ranging from 0 to 255. It's not going to just be all ASCII text. And it's not just that that's missing. If we come here and look at it as a hex dump, it's all legit. Oops, let's scroll down here to the bottom. You know, it's all just legit ASCII text. You're not seeing anything. You're not seeing FB. You know, you're not seeing any bytes like that. So that's odd for sure. Also, I would expect, let's see, if we come over here and we do Wikipedia list of, this is something I've searched for a lot, so this is why it comes up so quickly for me. This page gives us the magic numbers or magic bytes for all sorts of different file types. And so if we come down to PNG, we expect PNG to start with 8954E47, where 54E47 is PNG. We do not see that here. You know, if it was going to be a JPEG, I would expect it to start, I would expect to see like JFIF is what shows up there, or maybe EXIF, or even it would start with FF, which it does not, it starts with a Z. So this is clearly not an image. And so I'm going to actually, while we're here, we'll go through the rest of the streams, but I'm going to go ahead and just grab this and copy it to my clipboard because I have a feeling we're going to play with it. This is TLS, not interesting, nothing there. Another get, this time from windows.com. Again, it's very unlikely we're using, you know, Windows has been exploited and they didn't even tell us that. And that's the end. So we are going to focus on the TCP side, at least on that base64 encoded stuff. So if we do, we can echo that and we can pipe it into base64-D and we get a PowerShell script. You can tell up here this function decrypt string, like this is the function syntax for PowerShell. System convert from base64 string is PowerShell. This is looking like PowerShell. So let's grab this again and we can put it into mal.ps1 so we have it. And let's go ahead and open up VS Code and we can take a look at it. We can have our mal.ps1. Unable to find PowerShell. Yes, I do. We'll not worry about it. We're not going to run it, so we don't need it. Whenever I have a thing like this, and it's not that long, right? It's only 69 lines, but I like to just collapse the functions down because then we can sort of get a feel for what we're looking at. So now we're down to, we fit on one screen. That's nice. We have functions called like create AES manage object, create AES key, encrypt string, decrypt string. And then we have this body here that's going to use those. This filter actually is similar to a function. It's declaring a filter. We'll come back to that, but we'll come back to that. It defines a key. We have out equals resolve.dns, resolve DNS name. So it's going to get the text records for Windows Live Updater.com from that. There's our DNS server that we saw in the conversations. And so it's going to get those and save those as out. Then we're going to loop over out, or I guess the indexes of out. And we're going to get the string value that came back as the text as encrypted string. We're going to call decrypt string using the key on the encrypted string. We're then going to literally pass that into IEX. So we're going to execute whatever they send down to us. Then we're going to take the results and we're going to encrypt it right here using the same key. And then we're going to put it into parts 32. So that's what this parts is. And basically what we're doing is we're doing a loop here from 0 to the full length divided by 32. And basically then we're going to get these. This is basically fancy syntax to say, give me the data 32 bytes at a time. So then we're going to resolve DNS name, start Windows Live Updater.com to our server. Then we're going to loop over each item in PR. So that was our parts. And that's some white space here. We can do that, do that. Actually, let's come here. We can do all of these again. There we go. Okay. So now this is for each part. We're going to decrypt. We're going to decrypt it, execute it, get the parts, send start, then send. This is basically the domain is being built is the next part and Windows Live Updater.com. So we're going to send all the chunks one at a time. And then when we're done, we're going to hit end that way, Windows Live Updater.com. And that's it. So this is some DNS pull down commands, run them all, and get the data exfilled. And we can take a look in the PCAP to see if that matches up with what we're seeing. So we have DNS. Let's go back to the top here. Some of these things look kind of legit. So right here we have a query for text records from windowslibupdater.com. And if we look at the response associated with that, we can drag this out. Answers, there's 1, 2, 3, 4, 5, 6, 7 answers. Oh, right here, answers. And we can look at them, and the text record is a base 64 encoded string. So it's probably the encrypted data. So that looks like our commands coming down. And then you see right here a query to start.windows live updater, followed by now we have queries. We have queries to CC1C, 328, these blobs going there until we get to end. And then the next one is a start with some more blobs until we get to end, and then a start, etc. So this is cool. We're seeing this data go through. Now we just have to figure out if we can decrypt it. So to do that, we are going to have to write a script. So let's come back over here. We will create a code.py. We will start with our shebang. User bin env python 3. I always like to import. Actually, we won't do that. We'll just do. We're going to use Scapy. So we're going to use from scapy.all import star. Import star is a really bad pattern in Python. You really don't want to do it, but for Scapy, it's just kind of how you have to do it. So that's what we're going to do. We will read the pcap. So we'll say cap is equal to rd pcap, and that came from Scapy. And then we just need, I think it was called capture. Oh, yeah, it's right there. Capture.pcap. And now we can do for pkt in cap. So for each packet, let's say if pkt.has layer DNS, print pkt.summary. Give ourselves a starting place here, and we can jump back to our terminal. Python decode.py. We got lots of good packets here. These are all the DNS packets. That is looking good. Where am I doing there? I'm cycling through previous commands. Okay, that looks cool. Okay, so let's go back over here. There's two things we have to do. We have to get the text records that came back that one time, and we want to then get the start, stop query, the query stuff. I'm going to start with the commands. So that seems like a good place to look for. So let's do this. Let's see. What if we instead here we do, we're going to import, actually let's not do this. Let's put a breakpoint here. We're going to do this the legit way. We'll put a breakpoint right here, I think, yep. And then we can hit F5. It might pop up and ask you what profile you want to run onto, but Python script is one of the ones, so you can just use that. And that's going to run the script, and it's going to break right here. We can go to our debug console, and we can say pkt, and here's our packet. It's probably, this gray is probably hard to see. We have the full packet. Now this actually is one of the going for actual windowsupdate.com. So we're actually okay with this. Let's keep running a few times here. And we can come down here and try pkt again. This one is still there. We're going to cheat a little bit here. We'll stop and we're just going to know. So we're going to say if pkt DNS, so we get the DNS layer, has layer, and we're going to call it DNS response, put R and R. Now we're going to do that same thing. Let's run that again with F5. Parse the packet, and we get here. Did we reach it? Oh, here we go. So debug console, pkt, and this is still a response. So we can say pkt dot. I guess we're going to cheat a little bit more and say, what if we want to say and pkt DNS query qd dot q type, and so this is the query type. We just have to kind of know that 16 is what a text record is. And again, we could Google this. When I was solving it, I actually asked ChatGPT, and it gave me this. Kind of neat. It wasn't perfect. I had to update this a little bit, but this was this is definitely where I got it. In fact, let's just run this right now without anything. I'm going to run this. There we go, decode.py. And we get 1. There's only 1 text record response, right? So we're looking for things that have the response records and the query type is 16. And there was only 1 time we queried for that. This part's actually a little bit tricky. And this, I am going to go back here and put a break here because this stuck me for a while. And because what ChatGPT will tell you to do is to loop over, each like AN. So we'll say, they would tell you to say, over debug console, pkt dns.an, like this. And you can see in here, there's a lot of stuff. We can see we have all of the different responses, right? And there's each one of these is in a DNSRR packet, I guess, or layer. And so what they will tell you to do is something like, let's see, p in that, like to loop over each of those and get .rdata, because this rdata is what holds that, right? So in theory, I should get 7 rdatas here, but I only get 1. And I can't explain why Scapy doesn't quite work this way. But what eventually I figured out, and I won't bore you all with, by going too much into it, if we do pk packet DNS and we do an count, we can get, there are 7 answers. And so if we do like I for in, like that, and now here we're going to do pkt DNS.an sub I.rdata, like this. So now what we're doing is we're looping over we're looping over I in the number of counts. So basically it's, we want this to be a range, I should say. So now we're going to do 0 to 6 to do the 7. And now for each of those, we're going to get the rdata. And now we actually get each of those things. I don't know why, it feels like you should be able to loop over this AN, but it doesn't work. So it took me a while to figure that out. But so we can say for I in range pkt DNS.an count, answer count. And for each thing now, we're going to do a print pkt DNS an sub I.rdata. We'll save that. We will stop this decode or this debug, and we will run. We get them. Now they're actually each in an array for some reason, so we can actually do our data 0. They all look like they're of length 0. That'll pull them out. And now we have base 64 encoded data that needs to be decrypted. And so we're going to first say, so we're going to need from base 64 import b64 decode. We'll come here and we'll say enc equals b64 decode. Now we've got our encrypted data. Let's go ahead and make a decrypt function. Def decrypt, and we will take enc. That's really, I could have passed the key in as well, but I don't need to pass the key in. Actually, let's for the sake of, well, let's go look at what the encryption looks like. We know we're using AES. We know we're using AES, and we're going to create that with a, let's see, where's encrypt string? Here we go, or decrypt string, I guess is what we want. So we're going to get the bytes. The first 16 bytes are going to be the IV, and then we're going to create an object using the key in the IV. So the key is hard-coded here, which is going to have to be base 64 decoded. And then we get the IV, and then the rest of the data from 16 on is the encrypted data. So that doesn't look too bad. Grab this. Come up here, we can say key equals b64 decode that. IV equals, let's actually make this data 16. enc equals data 16 onwards. We're going to need AES stuff here, right? So we're going to do from crypto.cipher. It gave it to me. There it is. Cipher.import AES. Beautiful. Glad I remember how to do that. So now we can say AES equals AES.new. The key we have, and then we need AES.mode CBC because we saw that, and we need the IV. Then we can do plain text is equal to AES.decrypt ENC PT. And now if we come down here, we can say print decrypt ENC. No chance this works on the first try, is there? Let's see. Sweet, we actually got stuff. So this looks like it. We've got this zero padding at the end, so we can do something to get rid of that. Let's see. We'll do dot R strip. It's gonna be bytes x00 like that. That should remove from the right side null bytes. That looks good. We can also decode just to make it look a little nicer. Decode. Run that again. And here we go. So it wants us to run hostname, who am I, WMIC. It wants us to add a user and do some other stuff. Just this right here, this net user, default user with this thing, this password looks base64ish. And anytime you see something base64ish in a CTF, you want to decode it and see if it decodes. You might get junk, but you might get part one of the flag. So we have half the flag here. Running low on time, so we should probably speed this up. We need the other half. So we need to figure out how to get the other half of the flag. And it's probably going to be in the responses. So this part right here, come back up. This if right here is where we're checking for the type of text records. Now we want to actually look for queries going out, right? Because the queries are where they're exfilling the data. And so we're going to want to say something like if pkt dns.qr is equal to 0, and that's a query record. Oh, sorry, that's, yeah. And so, and we want to say is Windows live update per.com in pkt dns.query descriptor .q name. If we've got that, we want to do what? We want to really get, so we can like print pkt DNS. Let's just try that and see what happens. PTK not defined. Where did I put PTK? So here we go. We got all the different pieces coming out here. That looks good. We really just want this first part up to windowsliveupdater.com. So we can do, looks like that's going to be .qd.qname.split on the dot. Get this the first one. Let's see if that works. We hit some sort of problem. Oh, no, I could hit code. What? Not sure why that happened. Let's see. Bytes like object. Okay, so because we're splitting bytes, we have to split on a byte like this. So save that. We can also just decode it. So that looks good. In fact, we'll do that. We'll decode like that. All right, so we've got our stuff here. Now we have to handle these starts and ends. So what we're going to do is we're going to, we'll say if, oh, so we'll say that we'll do this. We'll say sub, like subdomain, is equal to that. And now we can say if sub equals start, data is going to be empty. Probably gonna have to initialize data up here too. Even just guarantee that. Elif sub equals end. We're gonna do we're going to print decrypt what is our, I guess, data, else, so if it's not start or end, we're going to do data plus equals sub, like that. We should probably, yeah, I guess that's good. Let's take a look at that and see how that runs. Whoa, okay. Object class cannot be passed to C code. Decrypt data. Ooh, let's see. What if we just look at what are we passing here? Because we want actually to pass bytes here. We might need a base, it was a base 64. The other data was base 64 encoded. Oh, this looks hex encoded. Okay, let's try that. We could probably just go over here and look. Get hex encoded up here. Oh, it probably comes back as hex from encrypt string. I don't know. We feel comfortable that looks like hex, so let's just deal with. Let's try it. We can do bytes dot from hex on our data there. Oops, this is not Vim. I don't need to do that. And let's try running it again. Bytes, did you mean from hex? Yes, I did. Thank you. Cannot decode byte. That's promising. And we got some sort of binary. Let's just do errors equals ignore. We could be throwing away some data here, but let's just, for the sake of trying to figure out what's going on, we're going to ignore for now. And that looks like it worked. So we still have our commands up here. And then here is our hostname response, our who am I response, our IP config response, antivirus product response. This net user probably doesn't add anything. Firewall stuff. Oh, but right here in our thing is part 2. We've got the other half of the flag. So we've got that. I'll leave this basically we can do a quick run through of the script again just to see it. Basically, we're looping through our PCAP, and for this part, we're saying if it's got a response and the query type is for 16 or text, I want to get that stuff. And then here we're saying if we're querying and it's Windows Live Updater is in the query name, then we want to check, and if it's start, we start a new string. If it's end, we're going to decrypt the string, and then otherwise we're just going to add to the string. And that's how we got our data. So being able to write some simple, simple, short-ish, this is only 30 lines of Python to do things like parse this is pretty important when you're being able to do CTFs. If you really are Python averse, you can always, gather it by hand out of Wireshark and then go to things like Chef will help you do this decryption, but learning how to script is a very valuable skill, so I highly recommend it. And with that, I'm going to go ahead and end this one. Thanks for hanging out with me today.